Assalamu alaikum. Welcome to a data structure presentation focusing on the segment tree. My name is Mohammad Hasan Kabir and I am joined by my teammates KAZI SARWAR CHOWDHURY, ABID UTSHA, Fahad MAHBUB and Mohammad SOHANUR Oman Sohag. We also like to thank our instructor Shadmim Sifat sir. Today I will be discussing the motivation and history behind this data structure. What exactly is a segment tree? It is a versatile balanced binary tree data structure. It is designed to store information about intervals or segments. The primary function of this tree is to answer range queries and update elements efficiently. What does this tree look like? Let's say we have an array. Segment tree is basically a tree built on top of the array where the root represents some type of range query, for example, summation of the entire array. To understand the motivation behind this structure, we must look at the core problem of dynamic datasets. Imagine we have an array of numbers. With this array, we have to perform two primary operations. The first is a point update where we need to change a value at a specific index. The second operation is a range query where we need to find the sum or minimum or maximum between indices L and R. The major challenge here is doing both of these operations efficiently on large changing data. For example, we might want to change the value of index 2 to 9 and to find the sum of indices 1 through 4. We have two approaches. An approach could be brute forcing our way through. For a point update, this approach works perfectly. It operates in big O of one time because it is a single memory address access. The update is instantaneous and requires no iteration. However, range queries are a different story. A range query here operates in big O of n time because to find a sum you must visit every element within that specific range. For a sum query of 1 through 4, we iterate from index 1 to 4 and we get 12. This linear time operation is far too slow for billions of queries on large arrays. To improve on range query, we can use prefix sum array, which is our second approach. We have the original array. For the prefix sum array, the current index holds the sum of all of its previous indices plus the current index. So we have 3 in index 0. Then for index 1, it would be 3 plus 2, 5. And 5 plus 4, 9 for index 2. And so on. This approach makes the range query incredibly fast, bringing it down to O of one time. You get an instant result with just one subtraction. For example, the sum from index 1 to 4 is simply the prefix sum at index 4 minus the prefix sum at index 0, which equals 12. But this efficiency comes at a cost for updates. A point update now requires O of n time due to a domino effect. If we update the original array at index 2 to a value of 9, all indices greater than or equal to 2 must be recalculated in the prefix sum array. This brings us to the ultimate performance trade-off. A standard array gives us O of 1 updates but O of n queries. A prefix sum array gives us O of n updates but O of 1 queries. The segment tree provides the best of both worlds. With a segment tree, both the point update and the range query operate at O of log n time. It strikes the perfect balance between update and query speed. Where did this elegant solution come from? Let's look at segment tree's history of creation. In 1977, Victor Klee asked the question: given a collection of n intervals on a real line, how do we compute the length of the reunion? He observed that an O of n log n solution follows from a sorting algorithm. Later that same year, American computer scientist John Bentley considered natural generalization to 2 dimensions. Bentley's goal was to compute the area of the union for a collection of axis-aligned rectangles. He developed a sweep-line algorithm that reduces the problem to n one-dimensional problems by sweeping a vertical line from left to right across the rectangles, creating a collection of intervals or segments. Bentley invented the segment tree data structure specifically to maintain the intersection of those rectangles and the sweep line. So how was the segment tree originally used? Whenever the sweep line hits the vertical edge of a rectangle, the segment tree is updated along with the running total of the swept area. But how did it transition from being used in computational geometry to competitive programming? Over time, competitive programmers made a crucial discovery. They realized that the underlying logic of the segment tree was absolutely perfect for one-dimensional array range queries, and that is how this fascinating data structure is most commonly used today. Thank you.
Assalamu alaikum everyone. Today I'll be talking about segment trees, specifically how they're structured, how they're stored in memory, and how the build algorithm works. Let's get started. Tree geometry. So what does a segment tree actually look like? It's a balanced binary tree built on top of an array. The root covers the entire array, say from index 0 to n-1. Every internal node splits its range into 2 halves. The left child takes the left half, the right child takes the right half. This keeps going until we reach the leaf nodes, where each leaf holds a single element from the original array. The height of this tree is at most log2 based n, and that's the key property that gives us fast O of log n queries and updates. On this slide, you can see a sum segment tree for the array 2, 1, 5, 3. The root holds 11, the sum of everything. As you go down the tree, each node holds the sum of its portion of the array. Memory representation. Now, how do we actually store this tree in memory? We don't use pointers or linked nodes. We store it as a flat, one-indexed array, exactly like a binary heap. The rule is simple. If a node is at index I, its left child is at twice I, its right child is at twice I plus 1, and its parent is at floor of I divided by 2. Index 0 is intentionally left unused. This is so the parent and child math stays clean and simple. You can see the array layout on screen for array 2, 1, 5, 3. The root sits at index 1 with value 11 and leaves are at indices 4 through 7. Space complexity. Let's talk about how much memory a segment tree needs. If n is a power of 2, we need exactly twice n minus 1 nodes, so an array of size twice n is enough. But if n is not a power of 2, the tree pads itself to the next power of 2, which can nearly double the size. So the safe rule everyone uses is always allocate 4n space. This guarantees no overflow for any value of n. It's simple, it's correct, and it's still O of n space overall. The next several slides walk through the build process step by step for a minimum segment tree on array 3, 2, 4, 5, 1, 1, 5, 3. The idea is divide and conquer. We start at the root with the full range 1 to 8 and split it in the middle. We recurse left first, going deeper and deeper until we hit a leaf node, where L equals R. At that point, we just copy the array value directly into the tree. Then as we come back up the recursion, we merge the two children for a minimum tree. That means taking the minimum of the left and right child values. So for example, at node covering 1, 2, the left leaf has value 3 and the right leaf has 2. So the node gets minimum of 3, 2, which is 2. This process repeats for every subtree, left half first, then right half, merging on the way up. By the time all recursive calls have returned, the entire tree is filled. The root ends up with 1, the global minimum of the whole array. These slides show every single call in this order, with the call stack shown on the side, so you can track exactly where we are in the recursion at any point. These slides show the initial setup of the segment tree in code, declaring the arrays, reading the input, and the sample input or output to illustrate what the tree is supposed to compute. Now let's look at the actual code, the build function that takes three parameters: the current node index, the left and right bounds of the range it covers. Step 1. Base case. If L equals R, we are at a leaf, so we store array of L in tree of node and return. Step 2. Compute the midpoint. Mid equals L plus R divided by 2. Step 3. Recurse on both halves. We call build on the left child with range L to mid and the right child with mid plus 1 to R. Step 4. Merge. Once both children return, we combine them. Here it's a sum tree, so tree of node equals tree of left child plus tree of right child. For a minimum segment tree, it will be tree of node equals minimum of tree of left child and tree of right child. The initial call is always build 1, 0, and minus 1, starting at the root with the full range. Recursion tree of build. This slide visualizes the full recursion tree for n equals 8. Each node in the diagram is one function call. Notice how the structure mirrors the segment tree itself, 4 levels deep with the leaves at the bottom. The merging happens on the way back up after the leaves are filled. In total, there are twice n minus 1 calls, which is 15 for n equals 8. Each call does only a constant amount of work. Time complexity proof. And that brings us to the time complexity. First, a segment tree for n elements has at most twice n minus 1 total nodes. Second, each call to build does O of 1 work, just one comparison, one calculation, one assignment, no loops. So the total work is O of 1 times twice n minus 1, which is simply O of n. Even though the tree looks complex, building it is very efficient, linear time, and that's the full picture from the tree geometry to how it's stored in memory to how the build algorithm fills it in big O of n time. Thank you.
This is Hasan. My teammate just showed you how the segment tree is built. Now, what do we actually do with it? My section is the range query, the core read operation. This is the whole reason the tree exists. Here's the problem. Given an array, I want the sum of elements between index L and R. For 5 elements, easy, just loop through it. But if the array has 10 million elements and I'm running a million such queries, a naive O and scan becomes a trillion operations. That's not viable at all. The segment tree solves this because the tree already holds pre-computed results for every interval. A query doesn't rescan the array at all. It just navigates and combines answers that are already stored. That's what drops the cost to O log n per query. Here's the function. Query node LRQLQR. The first three tell us where we are in the tree. The last two are the user's query range. Those never change. The entire logic is three cases. 1. No overlap. The node's range is completely outside the query range. Return 0, stop recursing. 2. Total overlap. The node's range is fully inside the query range. Return tree of node directly. We don't go deeper at all. The answer is already there. 3. Partial overlap. The node straddles the boundary, split at mid, recurs into both children, merge the results on the way back up. Cases 1 and 2 are our escape hatches. They are what makes this fast. Geometrically, the blue bar is our query range. A node's range is either completely outside it, completely inside it, or straddling the edge. Every single recursive call falls into exactly one of these. Let's run it. Array 2153. Query is sum of array 1 to 2. Expected answer is 6. Root covers 0 to 3. Query is 1 to 2. Partial, so we split. Left child is 0 to 1, still partial. Its left child 0 to 0 has no overlap, returns 0. Its right child 1 to 1 is totally inside, returns 1. The right child 2 to 3 also partial. Its left child 2 to 2 is totally inside, returns 5. Its right child 3 to 3 has no overlap, returns 0. Merging back up, node 2 returns 0 plus 1 equal 1. Node 3 returns 5 plus 0 equals 5. Root returns 1 plus 5 equals 6. Correct. Why O log n? Here's the key insight. Partial overlap, the only case that recurses, only happens at the edges of the query range. Every node in the middle of the range either fully contains the query or is fully outside it. Both cases terminate immediately. Per level of the tree, there are at most 2 boundary nodes on the left edge and 2 on the right. So 4 nodes maximum per level. The tree has log n levels. That's 4 log n nodes total, which is O log n. For a billion elements, that's about 120 node visits. Formally, height is log n, at most 4 nodes per level, each is O of 1 word, total O log n. Stack space is also O log n from the recursion depth, nothing allocated on the heap. So build function is O of 1, query is O log n every time, and this isn't just for sum. Minimum, maximum, GCD, XOR, any associative operation fits into exactly the same framework. We just change what merge means. That's range queries. Thank you.
Assalamu alaikum. In this section, I'll cover how a segment tree handles change, both single element updates and range updates. I'll also be showing an advanced optimization called lazy propagation that keeps range updates as efficient as everything else. Let's start with point update. The goal is simple. We want to change a single element at index k to a new value. The key insight is that we don't rebuild the whole tree. Instead, we trace one path from the root down to that leaf, update it, then re-emerge the parent nodes on the way back up. This way, only log n number of nodes are touched, which is why the time complexity is also order of log n. Let's trace it live. Our array here is 31411513, and we are calling update at index 2 with new value 0. We start at the root node 1, which covers the full range from 0 to 6. Since it's not a leaf node, we compute the mid, which is 3. Since our target index 2 is less or equal to mid, we recurse left into node 2. And now we are at node 2, which is covering 0 to 3, which is again not in leaf node, and the mid here is 1. This time our index 2 is greater than mid, so we'll go right into node 5, which is covering 2 to 3. Notice the call stack growing. We're building up frames we'll need to unwind later. At node 5, range 2 to 3, mid is 2. Our index 2 equals to mid exactly, so we go left into node 10. Node 10 covers 2 to 2, which is a single element, and since the left will be equal to right, we'll be hitting the base case. We set that tree node to our value, which is 0. Look at the second index here. We have successfully changed it to 0. Now we need to fix each of its ancestors. On the way back up, each node recomputes its value as the minimum of its 2 children. Node 5 becomes the minimum of 0 and 1, which is 0. And node 2 becomes the minimum of 1 and 0, which is also 0. And node 1 becomes the minimum of 0 and 1, which is again also 0. And all of these 3 merge operations cost O of 1 time. So now the tree is fully consistent again. The total cost of order of log n. That's the point update done. Now we face a challenge if we want to update every element within a range. If we try to add 3 to all values between index 2 and 5, The naive approach would be just to call point update for each index in the range. But if we follow that approach and the range has n elements, that's n times order of log n or order of n log n total. For large input, that completely defeats the purpose of having a segment tree in the first place. We need something more efficient. That's where lazy propagation comes in. Instead of immediately pushing an update down to every affected child, we store the pending change at the current node in a parallel lazy array and only propagate it downward when that child is actually visited later. There are mainly 3 steps. Mark the update at the covering node, push it down only when needed, and clean up by resetting the lazy value to 0 after pushing it. Down here, we can see how the push down handles the propagation and how the range update uses it. Now let's start visualizing it. We'll call range update on 2 to 5, adding 3 to each element. We start at the root node 1, range 0 to 6. The query range 2 to 5 partially overlaps. It doesn't fully cover 0 to 6. So we push down any existing lazy value and recurse into both children. Down the left side, node 2 covers 0 to 3, still partial, so we recurse further. Node 4, covering 0 to 1, has no overlap with 2 to 5 at all. We skip it immediately. Node 5, covering 2 to 3. Here is the key moment. 2 to 5 fully covers 2 to 3. So instead of recursing into node 5's children, we do exactly 2 things. Add 3 to tree 5 and store lazy 5 is equal to 3. The orange badge here on the node is the pending marker. Node 5's children are still untouched. Over on the right side, node 3 covers 4 to 6. Again, partial overlap. Node 6 covers 4 to 5, which is fully covered by our query range. So we'll do the same thing as before. Add 3 to tree 6 and set lazy 6 to 3. Node 7 covers 6 to 6. That's outside our range entirely, so we'll skip it. Now we have 2 nodes marked as lazy. 6 nodes visited in total. Now we'll be merging back up. Node 2 recomputes the minimum of tree 4, which is 1, and tree 5, which is now 4. So node 2 becomes 1. Node 3 will recompute the minimum of tree 6, which is 4, and the minimum of tree 7, which is 3. So node 3 will become 3. So now the tree is reflecting the current minimum at every level. But the lazy batches on nodes 5 and 6 still remain. Will be pushed down to their children only if and when a future query visits those nodes. That is the whole point. With deferred work we may never need to do. 6 nodes visited, O of log n in total, which is comparably less to that of n log n with the naive approach. So why is lazy propagation order of log n? There are 4 reasons why. The tree height is log n, so any path is bounded. And at each level, we visit at most 4 nodes for any query range. The rest are either no overlap, meaning skips, or full cover, meaning stops. The full cover is order of 1 work. If we multiply it out, order of log n levels times order of log 1 per level gives us order of log n for both range updates and range queries. The complexity table here summarizes the complexity of each operation, where point update takes log n time and range update with lazy propagation also takes log n time. Same with range query. That covers the point update and the range update using lazy propagation.
My team just covered the mechanics of the segment tree. Now I'll break down the macro architecture. We'll look at engineering trade-offs, compare it to other alternatives, and see where this actually runs in real-world systems. Let's start with performance evaluation. In system design, we constantly balance speed against physical memory. The main advantage of the segment tree is this is absolutely versatile. It naively supports non-reversible operations and stays perfectly balanced for highly dynamic data. But the drawback is its heavy memory overhead. To prevent allocation crashes, you must strictly allocate 4 times the dataset size. It also carries a stiffer implementation curve. So, where does this speed actually come from? It relies on 3 pillars. The first one is synthesize, merging pre-aggregated data with binary search for logarithmic queries. The second one is dynamic data agility. Unlike simple prefix array, it handles constant updates without breaking down. And third one is precision. Its explicit nodes guarantee every subrange is counted exactly once, preventing double counting in non-additive math. Given this heavy memory cost, why not just using a simpler alternative works? Let's compare. The most common alternative is the Fenwick tree. Fenwick trees are highly memory efficient. using only linear space. However, they are strictly restricted to basic prefix operations. On the other hand, the segment tree sacrifices memory to give you a total structural freedom, allowing complex queries and creating custom merge logics. So, why is provisioning 4 times the memory worth it? It's a structural necessity. While a Fenwick tree fails with non-invertible data, a segment tree's explicit node architecture holds complex, non-reversible data at every single level. That clarity makes the memory trade-off entirely justified. So now, stepping away from the theory, where does this logic run in the real world? In computational geometry, this powers the Klee's measure problem to calculate the area of overlapping rectangles. Paired with a sweepline algorithm, this segment tree instantly tracks and updates active interval as the line sweeps across the coordinates. Look at the database engines on the other side. Handling time series indexing, this uses it fantastically. If a system needs the maximum temperature in the last hour from millions of records, it cannot afford a normal linear scan. But pre-calculating aggregates, the database uses the segmented structure to return the answer almost instantly. We will also see it in geographic information systems. Whenever you zoom on a digital map, the engine executes a multidimensional range query to find exactly which roads fall inside your window. Segmented spatial partitioning allows that screen to render without any lag. So ultimately, the segment tree proves a key system design principle. Investing memory upfront unlocks a massive and predictable speed for real-time applications. Thank you.